Hello, I'm going to try and explain these new wireless crack attacks that have been the subject of much media coverage and speculation. So the crack attacks are a vulnerability in the WPA protocol. We use WPA for pretty much to encrypt all of our wireless networks. We used to use WEP, now we use WPA. And WPA has got this magical thing called the four-way handshake. And the point of the four-way handshake is to make sure that when your device connects to a wireless network, both sides can validate that they have the same key without sending the key over the network, and then also use that to derive another shared key, or set of shared keys, that they can use to encrypt data back and forth. So the shared key that both sides start off with is something called the pairwise master key. And if you think about your home network, if you've got a shared Wi-Fi password that everyone puts in, that's what the pairwise master key is, or at least what it's derived from. In your enterprise network, you authenticate with your username and password. PMK is generated for you, so that changes every time you authenticate to this network. That doesn't matter too much. So in the four-way handshake, there's four exchanges going by. So the first exchange, message 1, is the access point talking to the client. And in that, they send a bunch of random data called a nonce for short. So nonsense stands for nonce stands for nonsense. So that first nonce is called the A nonce, or the authenticator nonce, that comes from the access point. Then the client sends some nonce back called the S nonce or the supplicant nonce. Now these are just highfalutin words that the Editor 211 guys came up with, but effectively we're talking about an access point and a device. So both sides exchange this random data. And now both sides have the same random data, this A nonce and the S nonce, and they can initialize their crypto. And they do that by combining things like the SSID and this pairwise master key and these 2 bits of random data and a couple of other things in this crypto magic black box. And from it they generate a couple of things, but one of them is something called the pairwise transient key. So this is a temporary session key that will be used to encrypt communication between the access point and the client device for about an hour. Something like every hour this thing will get rotated. So message 1 and 2 are about sending this random data backwards and forwards. And then message 3 and 4 are about now using the generated pairwise transient key to encrypt some communications backward forward. The one is for the access point to send something called the group key to the client device. And the group key is used to encrypt communications that go to all devices rather than just one. So it's shared across all devices on the network until it changes. And the other is an acknowledgement. So message 1 is the access point sending random data to the client. Message 2 is the client sending random data back to the access point. Message 3 is the access point encrypting the group key back to the device, and the message 4 is the device sending an acknowledgement back to the access point. So after this four-way handshake, the crypto is initialized and encrypted data can go backwards and forth. So the key vulnerability that Matthew Van Hooft discovered is that if you resend message 3 and block message 4 from being sent back to the access point, you can trick a device into resetting something called the packet number or packet counter. So if you imagine this encrypted handshake, you've got message 1, message 2, message 3, message 4. What he does is he first sets himself in a man-in-the-middle position. Now, people have gotten really confused about that. This isn't a traditional man-in-the-middle. This is a man-in-the-middle at a physical level. Now, you can imagine that's hard to do in wireless. It's not like there's a cable you can plug yourself in between. So what he does is wireless networks operate on different channels, which are effectively different frequencies. Is he sets up a rogue or fake access point that looks the same as the actual access point on another channel, aka another frequency far enough away from the actual access point. Then he tries to trick the client into connecting to that one instead and relays communications between his fake access point and the real access point. But this stuff's encrypted, so you can't see any of that data. So typically this isn't an attack that would get you anything. So what he's worked out with this attack is if he prevents message 4 from being sent back to the access point, he can then trick the access point into resending message 3. Now this is a standard part of the protocol because wireless is a lossy medium. If there's somebody rolls a giant water truck between you and the access point, the message might not get through. So the access point, if it doesn't see an acknowledgement in message 4, will resend message 3. So what Matthew does is he blocks message 4 from being sent. So the access point thinks It was never received. The access point then resends message 3. So at this point, the attacker has two versions of message 3, both of which are legitimate and can be accepted by the client device. But and he's also got message 4 from the client, but he hasn't sent it through to the access point. So what he then does is he forwards message 3 onto the access point, onto the client device. The client device will send message 4 and start sending encrypted data. Now, WPA2 has something called a packet number, which is a way of differentiating between different frames and making sure that they're unique. Now, this is different from a replay counter, which is actually within the encrypted text. We'll ignore that for the moment. This packet number is used to initialize the crypto for each individual frame. And it's important because it is the only thing which changes across frames to initialize this crypto differently. Now, that's an important thing that we'll get to in a bit. So the net result is the device starts communicating with the access point, but actually the fake access point, because we're man in the middling, and sends some encrypted data with a packet counter number of 1. Now, you can let a couple of these go. So let's say 10 packets go past. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 packets with the incrementing packet numbers. Then what you do is you send the second message 3 that the access point had retransmitted to the client. And what the client does is it reinitiates its crypto. So it reinstalls that same key that it had before and starts communicating again, but resets this counter, this packet counter, back to number 1. And again starts communicating 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 frames go across. So now as an attacker, what you've got is let's say, hypothetically, 10 wireless frames that have gone across with packet counters 1 to 10, and then another 10 wireless frames that have gone across, different wireless frames, but with the same packet counter from 1 to 10. And you can then use this to break the encryption. So that's how do you break the encryption is interesting. So the encryption being used, there's 3 types of encryption being used. There's the RC4 cipher and TKIP. There's AES in counter mode with CBC HMAC, which is called AES CCM for short, which is the most popular. And then there's AES GCM, which is AES in counter mode with Galois counter mode. Now, in TKIP and GCM, you can break the encryption quite spectacularly, but we're going to put those to the side for the moment and just talk about the most common case, which is AES with CCM. So AES and CCM provides confidentiality and integrity of your communications as long as the random data used to initialize the crypto is not repeated. And maybe you can start seeing where this is going. So think of this crypto as a black box. And to initialize this black box, you need to have a password, a key, and you need to have some random data. So for each thing that you encrypt, you have a new piece of random data. And the reason you do this is because if you share the same random data across 2 different things that you encrypt with the same key, then it uses something called the same key stream for both of those. So if you use the same data, the same random data, the same key, and the same data, plain text data you're actually encrypting, you should get the exact same block. If you change that random data, then you're going to get 2 encrypted blocks which look different. And that's what you want, right? You don't want somebody being able to view communications going over the air, being able to try and figure out what this stuff is based on commonalities with frames. And so the way Wi-Fi makes sure that this random data remains random is they use things like the MAC address, and I think they maybe use some other elements in the frame, from the wireless frame, and then they use this packet number. Now, these are, for all the other aspects, these are things that you can pull out of the air from observing the communications. And that packet number, we've now been able to trick into repeating, tricking the client device into repeating by resending this message 3. So the missing piece that we need is we now need to know what some of the plain text is. We need to know what was encrypted in one of these packets so that we can reverse it to get the key stream. And then once we've got the key stream, we can decrypt other packets with the same packet number. Now, Matthew van Hoof does not go into any detail around that at all. So at this point, I start guessing. Now, we've seen attacks like this in the old days against things like WEP. And what they would do there is they would use ARP packets, because ARP packets are much smaller frames than normal wireless packets. So they're really easy to spot, even though they're encrypted, because you can go, well, there's a really tiny encrypted frame. It must be an ARP packet. Plus, we generally know what are in ARP packets. They're very simple frames. Networks share a lot of things in common. And so we can guess at the structure of an ARP packet. So what we can do is we can send message 3, wait for an ARP packet to go across, and let's say it's at packet number 3. We know that's an ARP frame. We can guess at what the plain text is. We can use that to get the key stream. Then we can reinitialize message 3 again, and the next frame that comes across at packet 3, now we don't know what that's going to be, we should be able to decrypt. And we can repeat this numerous times, because you can keep resetting message 3 to keep getting different sets of getting the key stream for different packet numbers. And so doing this a couple of times, you should get a bunch of key stream data for a bunch of different packets, which should allow you to generically decrypt data as long as you keep resetting this counter by resending message 3. Now that's my hypothesis about how he's doing that stuff for the ARP packets. He didn't go into any detail about that. The other problem we're going to run into is how do we get the rest of the key streams, since ARP packets are really small. I've got some ideas about how that can be done, but it's complete speculation, so I'm not going to go into it here. Okay, so his paper is really long and detailed because he also talks about a bunch of edge cases. So what I've discussed is the most simplest case. It's where the access point and the client will accept an unencrypted message 3 being resent multiple times. So he's got a bunch of different edge cases which revolve around cases where it'll only accept encrypted message 3s, in which case he abuses this race condition and is quite smart. He also looks at a bunch of different handshakes. So it's not just the standard 4-way handshake. There's the peer key handshake, there's the group key rekeying, there's the fast transition, and he's found weaknesses in all of those that allow the same attack to occur. So he's really found a class of attacks in this wireless protocol. But they all generally put you in the same place. You're resetting these packet counters for a specific set of keys so that you can get the key stream data. There's some devices are more vulnerable to this than other devices. For example, iOS and macOS and OpenBSD were originally a little less vulnerable, but he's hinted darkly that things like macOS and OpenBSD are now more vulnerable than we thought. He didn't mention iOS. But all of the devices are vulnerable to the group key attack, which can, for the most part, with a bit more work, effectively get you into the same position. So the claims like every wireless device are mostly true. The level to which every wireless device is vulnerable is very different. Then he also found another major vulnerability, which is that for some Android and Linux devices running a certain version of something called WPA supplicant, they had what they thought was a security feature built in where they would clear the memory where this pairwise temporary key is installed. So when you resend message 3 and it reinstalls this key, it actually reinstalls a blank key of all zeros. So if we know what that key is, we can effectively then decrypt all of the communications. And the video he has up on his website, crackattack.com, is demonstrating that worst case scenario. So he hasn't released the code yet. It's under embargo. Manufacturers are scrambling to fix this stuff. Some patches have been released. I think Microsoft and MikroTik have released some things. So we can't actually fully gauge the risk of this attack until we've got the code and tried it out. There are higher order encryption protocols which will save you for the most part. So even if an attacker is on the same network as you, things like SSL, if properly implemented, should prevent an attacker from breaking into your encrypted communications. But the if properly implemented is the tough part. There's lots of places where it isn't. For example, in his paper he used match.com, not in his paper, in his demonstration, match.com to break into that HTTP communications. So if an attacker has a man in the middle position on your network, then that's going to be uncomfortable. But we'll get the full assessment of the risk once he releases the code. So that's it. I hope that was useful for someone. If it was, please leave me some comments. If it wasn't, please also leave me some comments. I'm @Singe on Twitter, or you can mail me at dominic@sensepost.com if you want to talk about this more. Thanks very much. Bye.